But let's now talk about the main application of Kalman Filter in the eHealth domain. In the previous example, we used Kalman Filter to track the position and the velocity of a car in an ideal scenario running in a 1D space. Changing a bit the model and the system of the equation, we can easily extend the same problem, same set of the equation in a 3D space. For this reason, Kalman Filter has been largely applied in 3D motion tracking, especially in navigation system and self-driving car. In the eHealth domain, actually, all the application, all the use case that imply the use of a motion tracking system, most of them use Kalman Filter. For example, sport monitoring, I think that most sportive people that is listening to this lesson has recognized that over the last few years, many applications have been launched tend to track the position of the runner, at least in a 3D, someone in 3D, someone in 2D space. Most of them has used Kalman Filter to couple the inertial sensor inside the smartphone or smartwatch with the GPS. Another great use case is in rehabilitation. Many rehabilitation systems need to track the exact 3D position of the body part in the 3D space to have, for example, to have the assessment if the person is executing a movement correctly or not. This can be, for example, achieved by using a camera and coupling it with some inertial unit to track the accelerations. And actually, with a Kalman Filter, we are able to fuse this data to have a reliable 3D position of the body part. For this reason, the use case is rehabilitation, but we can generally say that Kalman Filter has a large impact in virtual reality domain.
Motion tracking is definitely not the only application of Kalman Filter in the eHealth domain. In this example, we've seen a use case presented in this paper where Kalman Filter are used for vital sign monitoring. Specifically, here, the paper tried to reconstruct a respiratory and a heart signal from 3 different sensor channels, namely magnetic induction sensors. So sensors are positioned here on the trunk and give this output here presented on the picture in the bottom of the slide. These represent the change of impedance of an inner coil of the sensor and is used in many environments to extract the respiratory and the heart activity. So the goal of the paper is, given these observations that are taken with this sensor, extracts the breathing and the heart signal and the offset of the 3 sensors. Let's see now how a Kalman Filter can help us in solving the problem expressed in the slide before. First of all, this is the equation of the linear model with noise, 2 noise here. And first of all, let's define what is the state. The state, as we said, are the signal, the heart signal, the respiratory signal, and the 3 offsets. We will understand in a moment what this V signal represents. So once we define our state, let's define now the observation. So what we can measure actually from the system. And the observation, which in the case is represented by the letter zeta, are the signal, the induction signal measured with the induction sensor. And here we have a time series representation. Let's now define the transition elements, so the 2 metrics, A and H. So to do this, we need to have a model. And the model here is the sinusoidal model that, as we will see in a moment, basically try to represent the signal, in this case, the state signal X, as a sinusoid locally. And we use a process that is called in some reference book, extended Kalman filter. So we express the state at time t plus delta t as an approximation as the state as times t plus delta t multiplied by the derivative in time, which is called VDT. VDT is then differentiated as well, and with the assumption that the xdt is a sinusoidal with the omega as angular velocity, we can express even the derivative of VDT in reference to xdt. I will not give any detail here, and if you're interested, please read the paper. But actually, what is important now is that we have this relationship give us the possibility to write down a matrix of transition A, which connect the time at the state at time k minus 1 to the state at times k.
So some of you guys will probably ask how this omega is determined. And the answer is simple. Basically, having assumed that our signal is locally sinusoid, we can, at every time k, we can infer from the signal itself the omega. And that will be used in a sort of feedback in the time at the next time step. In fact, as you can see,
as in this slide, there is a kind of feedback of the two omega to the Kalman filter. So let's come back now to our model. We have written the matrix A. We then don't have any input in this case, so let's ignore the input. What we miss here is the matrix H. And in this case, if you think that this is the state, we measure only the three impedance signals that are the overpose of the third signal, the respiratory signal, and the offset of the sensor. And in this case, we can write down the matrix A as depicted here. This one has coefficient that allows to do a bit of weighting of the two signals. So this is just to give you an idea of how the process of Kalman filter can be used to extract some vital signal from a set of sensors. Okay, this is the output of our Kalman filter. So here we have the heart rate depicted in time, the estimated heart rate, and here we have the respiratory rate in time. We didn't mention that this paper also holds on some ground truth, which is represented by a PPG sensor for the heart signal and a flow respiratory sensor for the respiratory signal. And here, you can see how, for example, this is the respiratory signal here, predicted by the Kalman filter, and this is the ground truth. And you can see that there is quite a kind of an overpose of the two sensors, of course, a limit of some error. So that is the application. I really hope you enjoyed it. And I think that now it's time to pass to the second part of our theoretical lecture, which is the decision fusion.